How does this particular species of spider walk the surface of water without falling through? Why do liquids like oil and water not mix? And what makes bubbles spherical? The answer to these and many other such questions lies in the study and understanding of the free surfaces of liquids. Now, liquids we know do not have a definite shape, and therefore they acquire a free surface whenever you put them into a container. And these free surfaces are associated with some additional energy which we are going to inquire about through this video. And this entire phenomenon of having additional energy as a free surface, this is known as surface tension. So where exactly does the additional energy of a free surface come from? To answer this question, we'll have to dig deep down to the molecular level and begin our discussion with the intermolecular force of attraction. This force of attraction is between any two molecules. And actually, we know that the intermolecular force of attraction between molecules of a solid is really strong as compared to that between the molecules of a liquid or between the molecules of a gas. So these forces that exist between two molecules of a substance are known as intermolecular forces. Now, intermolecular forces of attraction are of two types. The first one is the adhesive force and the second one is the cohesive force. The adhesive force comes into play when I am talking about molecules of different substances. For example, if I have water inside a beaker, then the molecules of the water are attracting the molecules of the glass beaker at the sides. In such a case, where I have molecules of different substances, for example, here it is water and glass, the attractive force between them is known as an adhesive force. And therefore, the definition of adhesive force is that it is the attractive force between two molecules of different substances. Similarly, then I can also say that adhesive force exists between the molecules of water and air, which is at the free surface of the liquid. The molecules of water and air will also attract each other with an adhesive force. However, if I go far away from the free surface of the liquid, inside the liquid, then we are looking at what is known as the bulk of the liquid. And in the bulk of the liquid, we'll see that the molecules of water are only surrounded by each other. And the forces of attraction between them is known as the cohesive force. Therefore, the cohesive force is nothing but the attractive force between two molecules of the same substance. And hence, these water molecules are attracting each other by the cohesive force. So what exactly is the effect of the cohesive and the adhesive forces? Adhesive force is the attraction between molecules of different substances, whereas cohesive is the attraction between molecules of the same substance. So if you think about it, every time I have a liquid in a container, the force with which the liquid attracts itself is the cohesive force, and the force with which the liquid attracts the container is the adhesive force. And then it's very easy to see that if the cohesive force is larger than the adhesive force, which means that the molecules are attracting each other more than they are attracting the container, then in such a case the liquid will not stick to the container containing it. And this is an example that we see in case of mercury. It doesn't stick to the sides of a glass, and even if you drop it on, say, a wooden surface, it's not going to stick. However, if the opposite takes place, that is, if the cohesive force is less than the adhesive force, it means that the molecules of the liquid are more attracted to the molecules of the container than they are to each other. In such a case, the liquid will stick to the vessel containing it. And this is a very easy example to find. It is so in case of water and glass. In fact, water poured on almost any surface will not roll away, it will stick to the surface, and this is an example where the cohesive force is less than the adhesive force. But obviously, the range of these molecular forces is not going to be infinity, and therefore we must define what is known as the range of molecular attraction. This range is the maximum distance between two molecules up to which the intermolecular forces are effective, which means that beyond this distance, they will not be able to affect each other. Using the range of molecular attraction, we then draw an imaginary sphere around each molecule, and this sphere is known as the surface of influence or the sphere of influence. By definition then, it is an imaginary sphere drawn around a molecule taken as the center with the radius equal to the range of molecular attraction. When a molecule lies well within the bulk of a liquid, it experiences cohesive forces of equal strength from all sides. However, when a molecule lies on the surface of a liquid, a part of its sphere of influence experiences cohesion due to liquid molecules, while the rest experiences adhesion due to air molecules. Obviously, then we can see that the number of liquid molecules shown in red is larger than the number of air molecules, and therefore overall the net force that the molecule feels is the force of cohesion acting downwards. Finally, then we ask, what is exactly a surface? The surface is defined by understanding the surface film. By definition, it is a thin film of liquid near the surface having thickness equal to the molecular range of attraction. Surface tension is then associated with the extra energy that the molecules at the surface have as compared to molecules in the interior. In order to find the magnitude of surface tension, an imaginary line is drawn at any point on the interface besides the boundary. We then imagine equal and opposite surface tension forces acting perpendicular to the line in the plane of the interface. This line is in equilibrium. To understand it better, one can imagine a line of atoms or molecules at the surface. The atoms or molecules at the top pull the line towards them in order to reduce their surface area, whereas the atoms or molecules to the top pull the line towards them, whereas those below pull it towards them. Overall, this line is in equilibrium but remains tight under the tension of these forces. The formula for surface tension is then given by the force acting per unit length of an imaginary line drawn on the free surface of a liquid acting perpendicular to it at every point and on either side of it. Thus, the force F divided by the length of that line will give us the magnitude of surface tension. The free surface of a liquid thus behaves under tension, almost like an elastic membrane. Imagine a balloon fitted over the opening of a container. On pressing down on the balloon, our finger experiences an elastic force. The free surface of a liquid behaves in a similar manner. Thus we say it resembles an elastic membrane. So we saw that by definition, the magnitude of surface tension is the force per unit length of an imaginary line drawn on the surface of the liquid. From this itself, you can ask the question then, what is the force due to surface tension? And from this formula, you will understand that the force will come out to be a product of surface tension multiplied by what is known as the effective length. Now, how must you understand what is this effective length? Suppose you place a body of a particular shape on the free surface of a liquid. In such a case, that body will experience the surface tension force. And therefore, the force that you will have to apply to pull that body away from the free surface is the force due to surface tension. And in magnitude then, this force will be equal to the surface tension multiplied by the length of the body which is in contact with the liquid. For example, if you have a circular thick ring, then you will find that the surface tension forces are acting on the inner side of the ring and on the outer side of the ring as well. In such a case, if the radius of the inner side of the ring is r1 and the radius of the outer side of the ring is r2, then the inner effective length will be 2 pi r1 and the outer effective length will be 2 pi r2, and the total length which is effective in case of surface tension forces will be 2 pi r1 plus r2, and when this total effective length is multiplied by the surface tension per unit length, that is by T, you get the force due to surface tension. And therefore, to always write down the formula for the force due to surface tension, you ask yourself at which length is the water or the liquid coming in contact with the body. Let's say, for example, then you have a circular plate. The circular plate does not touch the liquid on the inside like a circular thick ring. However, it touches the liquid on the outside. And therefore, the effective length will be nothing but the circumference of this plate. And if the radius of this plate is r, then the effective length is 2 pi r and the force due to surface tension will be 2 pi rt. Similar logic is applied when we try to write down the force due to surface tension for bodies of different shapes. For example, if you have a plane surface so that there is only liquid below and air on the top, then the effective length is nothing but the length of the surface, and in that case the force is simply T into L. However, if you have a thin ring, so thin that the inner and outer radii are the same, which we can say r, then you'll simply get 2 pi r on the inside, and then you'll have 2 pi r on the outside, and when you add them up, the effective length is 4 pi r, and that multiplied by T will give you the force due to surface tension. Similarly, if you have a square frame, you have a total perimeter of 4L on the inside and 4L on the outside, giving you a perimeter of 8L multiplied by T gives you the force due to surface tension. However, in case of a square plate, you only look at the outside perimeter because the liquid is not present on the inside perimeter, and therefore the effective length is 4L. In case of a rectangular frame, you have 2L on top, 2L below, 2B on the left, 2B on the right, and the same goes on the inside, and this gives me T multiplied by 4L plus 4B, and exactly half the perimeter will be counted in case of a rectangular plate. So this is how you can write down the magnitude of the force due to surface tension. Now we have already seen that as compared to the molecules in the bulk, molecules on the surface of the liquid possess extra additional energy. And we saw that these surface molecules are pulled downwards by a net cohesive force. And thus we say that work will have to be done to lift a molecule from the bulk of the liquid to the surface against this net downward cohesive force. This work done will be stored into the molecule as potential energy, and this energy is then known as surface energy. To understand the relationship between surface energy and surface tension, let's consider a horizontal liquid film stretched across a bar which is free to slide over parallel guides. Suppose that we move the bar by a small distance d. This causes an increase in the surface area of the film. Since the area of the surface increases, and since we have done this against the forces which were trying to decrease the surface area, the system now has more energy because some work was done against these internal forces. Let this internal force be F. The work done by the applied force is then simply F into d, that is force into the distance by which the bar was moved. From the conservation of energy, this is stored as additional energy in the film as mentioned. If the magnitude of surface energy is given as T per unit area and the extra area by which the surface was increased is 2dL, then the extra energy stored in the film is simply T multiplied by 2dL. But this energy is exactly equal to the work done and is therefore given as F into d. From this we see that T comes out to be Ft by 2dL. However, this is also equal to F by 2L, which is nothing but the definition of surface tension. Thus, the quantity T, which is the magnitude of surface tension, is also the surface energy per unit area. So we say that the magnitude of surface tension is equal to the surface energy per unit area of the liquid interface and is also equal to the force per unit length exerted by the fluid on the movable bar. So we saw that the work done in increasing the surface area of the free surface of a liquid is stored into the liquid as surface energy. And then we defined the relationship between surface tension and surface energy, and we said that surface tension was surface energy per unit area. But surface energy and the work done is the same thing, and therefore I can say that surface tension is also the work done per unit area. And from here then I can say that the work done in any case will always be the surface tension multiplied by the surface area. And therefore if I ask what is the work done if I'm blowing a liquid drop, then in such a case when I increase the area of the drop from 0 to a big drop where the radius of the drop is capital R, then in such a case the increase in the area is 4 pi r square because the drop is assumed to be a sphere. And if the increase in area is 4 pi r square, then you multiply that by t and that gives you the work done. I want you to take this moment to notice how I have found the work done in blowing this liquid drop. I simply multiplied the magnitude of the surface tension into the surface area that has increased due to the blowing of the drop. Similarly then, if I increase the radius of this liquid drop, say from one radius r1 to a new radius r2, then in that case the increase in the surface area would be 4 pi r2 square minus 4 pi r1 square, and this will give me the increment of the surface area, that is 4 pi r2 square minus r1 square, and this multiplied by capital T, which is the magnitude of the surface tension, will give me the work done in increasing the radius of the liquid drop from r1 to r2. By the same logic, if I try to break up this drop of radius capital R into n droplets each of radius R, then what you have to do is calculate how much the surface area will increase. I hope you can understand that when you break a big drop into small drops, the total surface area increases, and therefore you will find the increase in the surface area, and that multiplied by T will give you the work done in breaking the bigger drop into smaller drops, and that comes out to be 4 pi T r square n raised to 1 by 3 minus 1, where n is the number of drops into which you broke the bigger drop. And then of course the reverse happens if you try to combine all the small droplets into a bigger drop, and then I say that the work done in coalescing n equal droplets of radius r into a big drop of radius capital R is then given by W is equal to 4 pi r squared T n minus n 2 by 3, where n is again the number of equal droplets that were needed to make that big drop of radius capital R. Now so far we were only talking about the work done in increasing or decreasing the surface area of a drop. What is different between a drop and a bubble? The difference is that a drop only has one free surface, that is the surface lying on the outside, and therefore we were only considering the increase in surface area of the outer surface. However, when we talk about a bubble, in such a case, the bubble has a free surface on the inside and a free surface on the outside, and therefore in such a case, we will talk about the increase in surface area of the inner sphere and the increase in surface area of the outer sphere. And therefore the total increase in surface area when I blow a soap bubble from R1 to R2 will be double that in case of a drop. It will be 8 pi T R2 square minus R1 square, because I am considering the increase in surface area first for the inner free surface and for the outer free surface as well. Finally, we must understand that when we coalesce many drops into one bigger drop, what we're doing is overall decreasing the surface area. But where will this extra surface area go? It's not going anywhere. It is going to be pulled into the drop. And in order to pull in this extra surface area into a bigger drop, some work is done. And this work is manifested as a tiny increase in temperature, where I say that this increase in temperature is delta theta, which is given by 3T by J, 1 by R minus 1 by capital R, where T is the magnitude of surface tension, J is Joule's constant, small r is the radius of the smaller drops, and capital R is the radius of the big drop that you are forming. At the beginning of the video, while discussing intermolecular forces of attraction, we mentioned that a liquid like mercury does not stick to the vessel. And this sticking to the vessel is actually connected to the concept of the angle of contact. Now, the surface of liquid near the plane of contact with another medium is in general curved, which means that when you try to rest a drop of a liquid on the surface, the shape that this takes depends on what is known as the angle of contact. But in general, this surface, which is connecting the plane of contact with the other medium, is in general curved. And then we can see that the angle between the surface of the solid and the tangent drawn to the surface of the liquid, this angle, when looked at the point of contact inside the liquid, then this angle is known as the angle of contact. It is denoted by theta and is different for different interfaces and different for different pairs of liquids and solids. It has a unique value for a fixed pair of media. Thus, we can see that the value of theta will actually determine whether a liquid spreads on the surface of a solid or it forms droplets on it. We know that mercury forms droplets on the surface, whereas a drop of water will spread on the surface. And then it is obvious that the angle of contact is quite different in both the cases. And the conclusion we will make is that whether a liquid wets a surface or not depends upon the strength of the adhesive versus the cohesive forces as mentioned in the beginning of the video. And then it's obvious that if there is a large adhesive force, then the liquid will experience a greater force pulling it towards the surface as compared to its own molecules, and hence the liquid will stick to the surface, and this is known as wetting the surface. And therefore we say that water wets the surface because of large adhesive forces. Note that it is not that cohesive forces are not present, but in this case the adhesive forces dominate. On the other hand, mercury experiences a large cohesive force because of which the molecules stick to each other more than they stick to the surface, and hence it does not wet the surface. And from the diagram itself we can tell that in general it means that if there is a large cohesive force, the angle of contact must be less than 90 degrees as in the case of water, but if there is a greater cohesive force, then the angle of contact must be more than 90 degrees as is the case of mercury. So let's summarize the characteristics of the angle of contact. There are three distinct cases. In these three distinct cases, when a drop of a liquid is made to rest on a surface, we observe three different conditions. In case of a liquid that wets the surface, we see that the angle of contact is less than 90. The shape of the meniscus of such a liquid is concave, and as discussed, the relative force strength is such that the adhesive forces are greater than the cohesive forces. In such a liquid, the level in the capillary rises, and this is known as capillary action, which we will study shortly. And as mentioned before, such a liquid wets the glass surface. However, in case of a liquid that has an angle of contact equal to 90 degrees, the shape of the meniscus remains horizontal. In such a case, the adhesive and cohesive forces are equal in strength, and the level in a capillary tube of such a liquid does not change. Such a liquid, however, is also said to wet the glass surface. Finally, in case of liquids like mercury, whose angle of contact is greater than 90 degrees, the shape of the meniscus is convex and the force strength is such that the cohesive force is greater than the adhesive force. Such liquids fall in their levels in a capillary tube and are said to not wet the glass surface. Due to the property of surface tension, liquids, drops and bubbles have the tendency to contract their surface area. Because they are trying to contract their surface area, this increases the internal pressure inside the bubble or the liquid drop. And therefore, there exists a pressure difference between two sides of the free surface. On the inside and the outside, there is a pressure difference, and this is known as excess pressure. At equilibrium, thus we say that the pressure inside a bubble or a drop is greater than the outside pressure, and this difference of pressure between the two sides of the liquid surface is called excess pressure. This excess pressure exists only in case of curved surfaces. This is because in case of a plane surface, the component of the surface tension, which is always tangential, will have no component normal to the horizontal surface, and therefore the difference in pressure or the excess pressure comes out to be zero. However, in case of a curved liquid meniscus, for example like a concave or a convex meniscus, it is found that the excess pressure always lies on the concave side. This difference in pressure is given by 2T by capital R, where R is the radius of curvature of the meniscus. In case of a bubble in a liquid, there exists only one free surface because the bubble boundary itself is made up of the liquid, and therefore there is only one liquid-air interface. The excess pressure is then given by delta P is equal to 2T by R. However, in case of a bubble in air, the bubble now has two free surfaces. It has the interface of the liquid with air on the inside and the interface of the liquid with air on the outside, and therefore the excess pressure is double as compared to the bubble in a liquid, and it comes out to be 4T by R. The liquid drop has exactly one free surface, and hence the excess pressure is the same as it was in the case of an example of the bubble inside the liquid. Similarly, then the excess pressure for a cylindrical liquid surface is given by delta P is equal to 2T by R. For a liquid surface of unequal radii is given by T into 1 by R1 plus 1 by R2. And for a liquid film of unequal radii is given by 2T into 1 by R1 plus 1 by R2. One of the most important consequences of surface tension is the phenomenon of capillarity. Capillarity is the consequence of the pressure difference across a curved liquid-air interface, and its well-known effect is that a liquid that wets the surface, like water, rises up in a narrow tube in spite of the gravitational force. A capillary tube or capillary is nothing but a tube with a hole of very small diameter. And the phenomenon of rise or fall of the level of a liquid inside a capillary tube is known as capillary action or capillarity. To demonstrate, consider a vertical capillary tube of circular cross-section and radius small r inserted into an open vessel of a liquid that wets the surface. The most common such liquid is water. The contact angle between water and glass is acute, and therefore the surface of water in the capillary is concave. This means that there is a pressure difference between the two sides of the top surface. Thus, the pressure of the water inside the tube, just at the meniscus, that is, at the air-water interface, is less than the atmospheric pressure. Thus, the water rises in the tube. The increase in height inside the tube is known as capillary rise, denoted by small h. The increase in height, denoted by h, is given by the ascent formula. When the weight of the liquid contained in the meniscus is neglected, h is equal to 2t upon r dg, which is also written as 2t cos theta upon small r dg, where t is the surface tension of the liquid, capital R is the radius of curvature of the liquid meniscus, d is the density of the liquid, and theta is the angle of contact, while small r is the radius of the capillary tube. When the weight of the liquid inside the meniscus is taken into account, the ascent formula changes and is given by h is equal to 2t cos theta divided by r dg minus r by 3. It is important to note that if the liquid meniscus is convex, as for mercury, then the cos theta in the above formula is negative and the liquid will then fall inside the capillary. This is capillarity. So this completes all the concepts that I want to revise with you under the umbrella of surface tension. I hope that was an informative video. Please keep watching and thank you for watching this video.